Are position, yeah. I'll use position. Okay. And once we put a position on some shapes, we're actually linking algebra to geometry. So coordinate geometry is the link of algebra and geometry together in one. And you can see that when you start off with x's and y's straight away, and algebra is all about x's and y's. We have this thing is the very first thing you usually do when you deal with coordinate geometry, isn't it? What's that called?
Axes.
Okay, axes has a more fancy name.
Cartesian plane.
Boom, Cartesian plane, yeah. It's called the Cartesian plane. What's plane? What's plane mathematically? What does plane mean?
Flat surface.
A flat surface, yeah, a two-dimensional flat surface. And Cartesian? It's the guy who came up with it. Descartes, some French guy, Descartes or Descartes. Or my French is not good, but that's where the Cartesian cart comes from. He came up with this. So it's a two-dimensional plane where we can plot coordinates. You're well used to this. This is the y-axis, of course, and this is the x-axis. Each part of the Cartesian plane is called a quadrant, split into 4 quadrants. Where's the first quadrant?
Top right.
Top right. That's the first quadrant, yes. Okay, and where's the second then?
Top left.
Top left. Why does it go that direction?
It's going down. X-axis going down. Yes, yeah. That's what the x-axis.
It's going down.
Like numbers.
So it's going reverse. So you go from 1 to -1, and that's the reason why. Why wouldn't it go in a positive direction? Why wouldn't it just go clockwise? We're all used to everything going to the right or clockwise is the usual motion that we use. Isn't it?
Be special,
To be special. Yeah,
so.
possible.
First start off with the first quadrant is just positive numbers.
Yeah.
And then second quadrant is negative x, like you can use back down.
Okay, I don't think that. Does that explain why we'd go to the second quadrant? And why we wouldn't put the second quadrant here? I don't think so. Okay. Third is here, and fourth is here.
Is there an answer?
There is, of course, an answer, yeah. When we're drawing an angle, it's got to do with angles. When we're drawing an angle, you draw it off the x-axis, don't you? So you may have seen this in, I don't know if you would have done this, unit circle and stuff like that.
Yeah.
When you draw an angle, you talk about this as the angle, yeah? And as the angle gets bigger, what direction does it go? Yeah, it goes this way. So it's got to do with that motion of an angle going around in 360. So the angle is off the x-axis. It's not off the y-axis, and it doesn't go, that's like a negative direction for an angle. That's why it's that way. Okay, so that's the first, second, third, fourth quadrant. Okay, so that's an easy enough start. When we're given a point in space here, we can have, so a point over here, 2, 3, that's 2 on the x-axis, 3 on the y-axis. That's what we call a coordinate. You've done that before. There's a few different formulas that are related to Cartesian plane or coordinate geometry. What's the one maybe? Y is mx. See, what's that for?
Linear graphs.
That's a linear graph. Yeah, it's an equation of a line. Yeah. So equation of a line. We'll start with that then. Equation of a line. This is probably the most famous one. Yes. Y is mx plus c. And within that we have the letter m, which means what?
Slope.
Gradient or slope. Yeah. Okay. And how is the gradient or slope of a line calculated?
Rise over run.
Rise over run. So rise over run. So that's the rise is the change in which axis? Y, yes. So that's y change, if you want, over the x change. Okay? So if we have in general 2 points, let's put one here. Let's call it x, y, and if that's the first point, we can call it x1, y1. And then we have a second point here, just randomly, x2, y2. How would I calculate the gradient between those two? Now let's say they're not exactly on these points, so we're not sure. How would I calculate the gradient?
y2 minus y1 over.
Okay, what is that formula doing for us? y2, so you're regurgitating this one? Yeah, it's finding the difference, yeah. So the difference between the two y values, so it does this calculation for us. It says how high up on the y-axis the two of them are. This one's at y2, and they subtract these two, and you get this difference. And then you subtract it the other way, and you get that difference. And that creates a slope for us, the rise over the run. Okay, yes, so that's the famous slope gradient formula. To get halfway between 2 points, what do we do? Yeah, so finding the average. So what's the average between these two x values? Well, it's about, on the x-axis, it's about here, which is, how would I get it, an average of two things? Yeah. So the midpoint, or the halfway point between the two, is going to be x1 plus x2 and averaged, and y1 plus y2 and averaged. So we do that to get the midpoint between 2 points. Which can be convenient when we're doing stuff like perpendicular bisectors. Perpendicular, 90-degree angle. How does perpendicular work with slopes or gradients? Okay, so if the gradient of line 1 is minus a half, what's the gradient of a perpendicular line to that? Perpendicular to line 1 is just 2, or 2 over 1, it's the exact reciprocal and different sign. They have to multiply to give what number? No. They'll multiply to give 1, but it's not positive 1, is it? It's going to be, if one's positive and the other's negative, it's definitely going to end up being negative. So, with perpendicular lines, the slope of one multiplied by the slope of another always gives minus 1. So that could be a test for perpendicular lines. If you know there's slopes of 2, multiply, you'd know anyway by looking at them. And of course, parallel lines have the same slope. All right. Right, let's raise a bit of this and get talking about equation of the line a little bit more. We have all that. Okay, so this is our standard equation of a line. There's a couple of ways of looking at this. Maybe we start off by looking at if we have one. So we have y is equal to 2x plus 3. Would we be able to draw that instantly? Yeah, where would be my starting point? 3 on the y-axis. Yes, of course. So the c of this c is where the y-intercept of the... So this is going to definitely cross at 3. And what would be my next step into sketching this? Okay, so you're extracting what the gradient is. 2 over 1, we're saying that for every one it goes over, it runs over 1 and rises up 2. So if I had a scale better drawn here, it goes 1 over and then up 2, and then that's the next point along the line. That makes sense. Okay. And then once I have 2 points, I can always draw a line. And it will continue with that slope forever. How do I know if a point is on the line or not? Let's say a random point in space. I'm not too sure, is 5, 10 on this? Is 5, 10 on that line? So you'd sub it in? Yeah. So in order for, it's a system, it's a formula. This is an x point, this is a y point. It will have a point at 5. We're just not too sure what the y one will be. Well, we probably could figure it out in a second. So is it on the line? No. Or you could test it out. 10 in for y, 2 times 5 plus 3. So we get 10 is equal to 13. Of course, that is not true, so that's not equals. Whoa. Not equals, and therefore not on the line. So if it was on the line, you expect that to be equals. Okay. All right, so you're able to draw it in that form. What happens if we give it in standard form? What's standard form? What shape? What does that look like? So this is what's this? This is called slope or gradient intercept form, or slope intercept form, depending. So what's standard form then, or general form?
0 equals.
So 0 equals,
So nx.
which way does it go? Does it go x, y, then the c, or does it go y, x, then the c, or does it go, so there's a few options for general form. It can go, let's say it's 2x plus 3y is equal to 7. Is that it? Is it 2x plus 3y minus 7 is equal to 0? Is it 3y plus 2x minus 7 equal to 0? Which one is it?
The last two don't make a difference.
The last two don't make a difference?
Yeah.
No. Well, none of them really make a difference.
Yeah, it's just.
They're all just rearrangements of the same thing. You could bring the 3y over.
Oh, yeah.
I think it's this one.
So wouldn't they all be right then? Yes, they are.
They're all right, like one different way to say it.
Yeah, technically they're all right, but standard form has its own, or general form, not standard form. General form, you're expected to be able to give an answer in general form. As in, they'll in the IB they'll go give your answer in general form, and only one of these is general form. It's the first one. This is general form. Now, I've never seen them take marks off. I would give all, but technically it's the first one. Technically. Okay. We won't worry too much about that, as long as we're able to use it. Why is it in this order? It's just decided. There's no particular, as you saw, it doesn't really make a difference what order it's in, but that's what has been decided as general form. Okay, so how do I draw that one?
You have to simplify it. Get y by itself first.
Okay, yeah, you're going to rearrange it to get this form. Is that what you're thinking? Yeah, that's a good idea. Is there another way we can do it? Yeah, so one option, yes, rearrange y is mx plus c, yes. What's the second option? How about if I asked you to find the intercepts of this line, the x and y intercepts? Yes. Okay, so use the intercepts way. Let x equal to 0, find y, and then let y equal to 0, find x. So if we let x equal to 0, we get 3y is equal to 7, and y is 7 over 3. And if we let y equal to 0, what's x going to be? Yeah, 7 over 2 or 3.5. Okay, and maybe it's easier, maybe it's not, but it gives you more information that you didn't have already. So it crosses the y-axis at 7 over 3, which is about here, and across the x-axis at 3.5, which is about here, and it's a downhill one. Okay, and that's another way of sketching it. You can rearrange it, of course, yeah. This one is probably slightly more preferable when you get this type of one. I don't know, maybe. Because dealing with a slope off a point that's not perfect. So you see this crosses the y-axis at 7 over 3. So to count over and up off that, 7 over 3 can be a bit awkward, but not necessarily incorrect, it's just a bit awkward. I would probably use this one. for the more tricky ones. Okay, have I forgotten anything? Oh yes. This formula. Have you seen this before? For the equation of a line? Okay, so this is given to you in the formula booklet. This is the equation of the line formula. It's another way of working. What bits of information do you think are needed for this? To fill in? Yeah, so you have a point and a slope. x1, y1, and the slope, well. If you have these two bits of information, you can get the equation of the line using this formula. Point slope. Some people actually call it point slope formula. So for example, if I have the point 2, 3, and slope minus 2, the equation of that line would be y minus, so this is x1, y1. Y minus 3 is minus 2x minus, what was x1? 2. And then I tidied that up. I'm going to leave it in point slope form. 7, yeah? 7, yeah. And that's across the y-axis at 7. Okay, so that's another formula that you may use. It's the equation of the line formula or point slope formula, whichever one. So there's two main ones. This is called gradient intercept form, this one. Okay. So when two or more linear equations, these are linear equations because they form a line, interact, it's called a system. And you've dealt with systems of linear equations already. You probably call them something different. When two or more linear equations interacts, you did it in GCSE, definitely. What did you call it? Intercept? Yeah, it's an interception of two lines, but there's a whole part of algebra that you dealt with that began with S. Yeah, simultaneous equations. Yeah, you solved them simultaneously, but they're just linear equations interacting, and you would find the point of interception using some simultaneous equations methods. So simultaneous equations are a system of equations. So that's two or okay. They're quite simplistic models if you're ever trying to use them in the real world. So we're only going to be looking at two lines interacting, so simultaneous equations. But we will move on to looking at three interacting in this unit. So only two today. So it's a very simplistic model of where that would happen in real life. Anyone think of an example? I know that's probably not something you think about every day. How could you model two real life, like business examples with two linear equations?
Like change on two different things.
Yeah, this would be something that's constantly changing at a constant rate. So the gradient would have to be the same, obviously, because it's linear. So it's something that changes constantly, maybe with time or distance. Okay, a good system or a good example is two taxi companies that use different amounts per kilometer but have a different set fee once you enter the taxi. So let's say taxi company 1 Oh, taxi 1 has a set fee of, let's say, $10, and then it's $3 a kilometer. And taxi company 2 has a set fee of $5, but goes at $5 a kilometer. So the classic is which is better value, and at what point are they the same value, and then which is better value after that point. Just by looking at it, if I had a journey of 4 kilometers to make, which taxi company would I take? 4 kilometers. What are you doing? You're saying your set price at 10, multiplying that by 4, you get 12, so 22. Set price of 5, multiply this by 4, 20, and you get 25.
So the $5 a kilometer is the slope, and the $5 is the y.
Yeah, is the y-intercept. Yes, exactly. So you'd actually take taxi 1 because it's a bit cheaper. Yeah. Yes, you're right. But you can plot this very easily. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ah, it's going to go off my scale, but you can see what's going to happen. If I went up in 2s, 2, 4, 6, 8, 10. Hi, Cleo. Hi, Cleo.
I'm sorry. I don't know where Mr. Michael upstairs?
Yeah.
First one or second one?
This one.
Okay, thank you. Sorry.
No problem. All right, so taxi 1 starts at 10 and goes up 3, which is not great. So let's say here, 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 here. And taxi company 2 starts at 5, but increases so much quicker. The second point is here, and you can see that this line is going to go up steeply, and this line, and they cross at that point. What is the crossing point? Yes, yeah, but what is it? Like, how many kilometers? How many kilometers does one become better value than the other? What's the exact point? How can we work it out? Okay, so taxi company 1 we can demonstrate as an equation. So it's 3x plus 10. And taxi company 2 we can demonstrate as equation 5x plus 5. Where do those two lines intersect? We would use a system of equations or simultaneous equations. We can use substitution, or we can use elimination. You know both those methods, I presume. Which is the easier in this case?
Substitution.
I would say substitution, because we already have y equals in both of them, so I can just replace, if I combine, so I'm going to use substitution, that I could say 3x plus 10 is equal to 5x plus 5. You happy with that? The y's are equal to each other, so I can let them equal. I've quick solution, 3x, subtracted from both sides. The 5 comes over, we're left with 5 here. So many kilometers in? So at 2.5 kilometers, taxi company at 1 becomes better value after 2.5 kilometers. Okay. So that's where two linear equation meets. That's an example of how it could happen in the real world. Very simplistic. More likely, you're going to get something with quadratics or a different form of function. Logarithmic is used a lot in this kind of business model of like plane journeys or taxi journeys, where it makes this kind of shape.
Yeah, we had one of our paper 6.
Oh, you did? Oh, awesome. That not awesome. It didn't go well.
No, I think that one